All right, because we're already running late. Dan, you're a neighbor, you're awesome, you're my friend. Give him a huge round of applause, the biggest one for any speaker, Dan Kaminsky.
Okay, is this mic working now? Excellent. All right, so we're gonna talk about something that's like sucked since 2002 and turns out it doesn't like fix itself or anything. We're gonna talk about PKI, public key infrastructure. How did I get playing with this? Well, it's about my 10th year doing research talks into fundamental design of the internet. So I've been looking at SSH and DNS and TCP/IP and DNS and web browsers and anyway. I was pretty sure there'd be nothing to do with DNS in here. Not that I wasn't wrong, but here's the deal. We right now on the internet have crap for security, and you all know it's true. The #1 reason, in fact, according to statistics, for all the elite O-Day attacks that we all find and all look into and all hear about, 61% of actual compromises in the field just come from passwords. From no passwords, from default passwords, from shared passwords, from my passwords. You could not design a technology that has blown up more in our face if you tried. So why do we keep using them? Well, they have this nasty little habit of working. Passwords are used because they scale well when you just have a small number. The human memory has a capacity. It can remember these things, and a few of them, and so people will use them. Where you get into problems are when you have lots of things you need to authenticate to and lots of passwords to use, because then the human memory starts to fail. Now, there are two schools of thought about what we do about passwords. The first school of thought says, let's at least make it so when you someone loses one password, it doesn't affect their other 30 servers. And the only way we can do this is if we either machine generate passwords or at least make passwords that look like they were machine generated. So you get like leet speak as a security technology. I'm just gonna say, the bad guys have totally figured out there's a relationship between S and $. They got it. So, this doesn't work very well. What we should be able to do instead is we should be able to get humans out of the memory business entirely. We should be able to have little pieces of hardware that actually do asymmetric key exchange, really interesting RSA and DSA technology. This should work. We have this, we've been building terabytes of hard drives, and passwords are what, like a couple bytes? Like, come on, we should be able to automate this. And what we were supposed to have, and what the vision of the future as of the end of the 90s, also known as the era we didn't know anything about security, what we thought we were building at the end of the 90s was systems for doing smart cards, where you don't type in a password, you just type in maybe a PIN number, a 4-digit number, into your little card, and your card does all the authentication magic. And the underlying technology that was supposed to make this work was supposed to be something by the name of X.509. So I have to apologize. I am blatantly committing copyright theft here by including this in my presentation. I did include the signature. And here's why. This right here is internet security at the end of 2009. If we only cared enough, we could totally ride this pony. So let's talk about reality for a second. Everybody loves blaming the business guys for why we don't have certificates and smart cards and this and that. We basically say the reason we don't have good security is business just doesn't care enough. You know, business has invested hundreds of millions of dollars in this crap over the course of the last decade. Something doesn't work. And what I tell you that something is, it's not business rules, it's we screwed up the engineering. X509 has something wrong with it. So this shouldn't come as a surprise. We have learned a ton about security, real-world security, in the last decade, but none of that knowledge is really baked into X509. It couldn't be. We finished that 10 years ago. We actually are right at the edge of being able to start over from scratch. DNSSEC, a technology which, as of a year ago, I thought was totally worthless, turns out actually does a lot of things better. It is a superior foundation. It is ultimately right in all the ways that X509 is wrong. I'm going to explain now what I mean by that. Before I go into that, I do want to point something out. We have been doing a lot of things wrong. There are those who say, well, if we've been doing things wrong, clearly this means we need to start over with like a totally new internet, and this one will be secure. Bullshit. Not how the world works. It's like saying we're going to have a city with none of the old problems of old cities. We're going to have like all new widths of roads and heights of bridges, and everything will be great, and we'll stick it in the middle of a forest with no roads or flights coming in or out, and it'll work great. No, it won't, because it won't be connected to anything. The reality is that migrating yourself from an insecure state to a secure state does not go through the path of absolutely starting from scratch. It goes through the path of taking individual components and migrating them over and exploring the network effects of that change without saying, hey, let's do a new internet. Yeah, sorry guys, you're just trying to get a whole bunch of funding. You know it and we know it. So let's talk about X509 again. X509 is the identity system behind PKI. It's used in SSL, it's used in IPsec, it's used in pretty much everything except for SSH, and some SSH implementations will use X509 as well. The best way to understand this technology is to think of it like the passport system. Look, I'm an American, and I'm out here in Germany. Germany as a country has no clue who Dan Kaminsky is, but it does know who the United States of America is. So Germany as a country gets an assertion from the United States of America saying, the person with this face has this name according to the United States of America. This is roughly what is going on with the certificate. You get an assertion that the person with this key material is this website name according to VeriSign. It really is nothing more complicated than digital passports. So in the real world, X509 has only one scenario where it has actually worked. I'm sorry if you're an actual X509 engineer, it's true. The only thing that's actually worked at any sense of scale has been SSL. And that's mainly been because the user interface actually pops up all kinds of alarms. SSL is a technology used to secure the web, to secure specifically HTTPS, for various definitions of secure. This is a miracle that happened in the late 90s. The late 90s, people realized this internet thing could totally make us money if only people would put their credit card numbers on the internet. Now, how do we make it so that the geeks don't scream bloody murder? And by a historical quirk, the geeks had figured out enough of crypto to say, if you do actual good crypto, good encryption algorithms, good asymmetric crypto, good this, good that, and this newfangled X509 thing we got, If you do all of it, we won't complain when you tell users to put credit card numbers on the internet. And I swear to God, I swear to all of you, that's the only reason we have strong crypto in every single user's desktop today. So this is a success story. However, it's not that great a success story. We've got about 1 million SSL endpoints on the internet. Let me tell you, you have a lot more than 1 million servers on the internet. And it turns out only about half of those are actually secure, meaning they're actually assertions by anyone. There's this very weird concept in SSL called self-signed certificates. Instead of having a passport that says, the person with this face is Dan Kaminsky according to the United States of America, it's the person with this face is Dan Kaminsky according to Dan Kaminsky. And worthless. So let me walk you guys through the actual real-world reality of what it takes to get an X509 certificate. So the first thing you do in X509 is you go over to DNS. Oh, you didn't see that one coming. So you go over to DNS and you register a name in there. And you actually provide in DNS a canonical user behind your domain. So if you say, this is the mail server, if anyone's ever going to send mail to docsparrow.com, here's where that mail should go. This is step one. You do nothing with crypto. First, you got to get your name, and you get that from DNS. Then you generate a public and private key pair. This is basically like building your face. What's that? Oh, no. So you build your face, your real face, then you take a photo of it, so that's the picture on the passport. Those are your private and public keys. You then go to a certificate authority. This is VeriSign, or in the analogy, the State Department of the United States of America, or wherever you do it in Germany, or wherever your particular nation is. So you go there and you say, hi, I claim to be the controller for www.docsparrow.com. And this is actually done with what's called a PKCS10 request. Now, the certificate authority could be talking to anybody. How does it know that you're actually the controller of docsparrow.com? Well, what it does is it goes to DNS. And it says, hey, DNS, what's the mail server I should go to make sure that I'm actually talking to this person? And then it goes there and it sends it an email. And if you come back and you say, oh, yes, I got that email, I got your secret magic code, it's me, then the certificate authority is satisfied that you are the correct identity, and it issues you the certificate. The basis of this trust, I'd like to point out, is already DNS. We already crossed that line many years ago. They never tell you that one, do they? It's kind of that step zero before. So now what I just described to you is something called domain validation. I'm kind of cheating because there are certificate authorities out there that are run by a bunch of paranoid bastards. I know because I get on the phone with them every once in a while, and these guys are afraid of everything. It's wonderful. And, you know, these guys, they're not going to just depend on DNS. They're going to do, like, DUNS lookups and phone calls. They're going to send a lawyer to your office and, like, get a blood sample. Like, there are totally certificate authorities that don't do just this. And it doesn't matter because there's no exclusion. There are dozens and dozens of certificate authorities out there that are trusted by the browsers. Every certificate authority can issue names that every other certificate authority is issuing names for as well. So if you get a certificate from Super Paranoid Guy, that's nice. The bad guy just goes to Jim's Certificate Shack. This is the direct equivalent of Zimbabwe being able to issue American passports. I'm not saying I don't like Zimbabwe, but it's not a good idea. So what this means is that everyone who does a better job as a certificate authority is actually penalized by the underlying technology The underlying technology creates a race to the bottom scenario where everyone has the same goodie to give out, and the only question is, who is someone going to go to get that goodie? If it's a big pain in the ass from this guy and it's really easy over here and it's the same output, well, I'm going over there. So the underlying technology is what has failed us. And anything more than the bare minimum, it's just security theater. There's literally no security value win to going to the paranoid people when the lazy ones have the same output. So DNS does not actually have this trait, and that is fascinating to me. I had no idea this system was so complicated. But check this out. In DNS, you have 3 layers. You start at the root. First of all, there's one root, not 300. There's one DNS root, and it is synchronized, and it has been running there for 20 years, and it'll be there 20 years from now. You tell me what else on the internet has that kind of long lifespan of a foundation. There's nothing. So there's one root. And do you have any idea what kind of a pain in the ass it is to get anything in that root? This is the least efficient of all possible governmental entities. You can't get things into the root if it's legitimate. Screw if you're a hacker trying to break something in. So there's this wonderful quote by Peter Gutmann basically saying the CA system is only as secure as the money they refuse to take. The root, it turns out, is part of the state system, meaning it's part of the system that creates money in the first place. That is a really unique trait. Now, it would suck if every time you had foo.com, bar.com, duxbury.com, whatever, you had to go to this intergovernmental entity because you'd never get anything through. But let me tell you, there's one thing governments are reasonably good at doing, and it's delegating. What the root does, and what the DNS technology allows, is the delegation of top-level domains to individual companies. VeriSign controls all of COM. Not 20 or 30 companies control all of COM. VeriSign. There is one entity that controls COM. There is one entity that controls org. There was one entity that controlled the top-level domain, which I'll leave unnamed, which was basically 90% malware. And what was happening was people were banning the top-level domain everywhere. They were just doing it by default. And this started impacting the revenues of the company that controlled the top-level domain. And you know what they did? They did exactly what we here would want them to do. They went ahead and massacred 90% of the names in their top-level domain to protect the revenue stream from the other 10%. This is what happens when responsibility and authority align. This is actually awesome. But you know, it would be a problem if there was only one company that I could go to actually deal with web interfaces. Let's say there was only one company. Let's say I had to go directly to VeriSign to put something in COM, and only VeriSign. And let's say VeriSign had a really crappy website, let's say. So let's say that happened, and you just had to accept if you have a COM name, well, you just have to deal with the fact that that SQL injection vulnerability applies to you too. Well, it turns out, in one of the smartest moves that I can imagine, they said, we're going to have only one company control the top-level domain, but we're going to allow registrars. We're going to allow resellers of names. We're going to put an extra layer here that controls the web interface, that controls the customer relationship between all the users and the single top-level domain. So even though you get the advantages of one company with all the responsibility and all the authority, the actual work of dealing with customers and providing the competitively best experience to you is actually distributed to only one person at a time. So a while back, Microsoft had their New Zealand names hijacked at the registrar. A little bit later, Comcast had their names hijacked at the registrar. Just recently, Twitter had their names hijacked at the registrar. This has turned out to be the most common way a domain name gets hacked if it's a corporate name. But this is what's awesome. All those companies can leave. They can say, you know what, this company I've been using, you suck. I'm going to give my money to Mark Monitor. I'm going to give my money to Ultra DNS. I'm going to give my money to somebody else unless you get your act together. You don't have that option in X509. If VeriSign screws up, okay, you can go ahead and get a certificate from Komodo, but VeriSign can screw up again and again and again. It's only in DNS that DNS can say, well, sorry, the registry no longer accepts any information about that name from you schmucks. It's only going to accept information from you guys over there. This is awesome. So, when I said you could not exclude a bad certificate authority, that's not entirely true. It is possible, this is the little fig leaf of possibility, it's the lie we tell ourselves to make us happy at night. It is possible to exclude untrusted certificate authorities. And what you do is you run your own private enterprise certificate authority. It's like your own private passports between you and your friends. It's very expensive, it's very difficult to maintain, and shockingly enough, it has fundamental issues every time you need to interoperate with someone at another certificate authority. Now, the United States government actually has made this crap work. They built what they call the Federal Bridge CA. It allows all the branches of the US military to authenticate to one another. The people who made this work deserve a medal. Okay, I'd like a system I don't deserve a medal if I get it to frickin' work. I'm just saying. So, what a lot of people thought, and this is late 90s cluelessness, they thought that interoperability with other enterprises was an edge case. It was a strange thing which usually you don't have to do. Every once in a while it'll be hard work, but you know, whatever. 99% of the time you're just authenticating to a resource in your own company. And not true. The reality is cross-organizational authentication is the rule and not the exception. First of all, every company has 83 million alliances with other companies, with vendors, with contractors, with customers. Remember those guys? Not to mention interactions with other groups. Anyone who thinks a large company is only one company has never actually worked at a large company. Yeah, like you hear like the smattering of laughter. Those are the guys who are like, oh God. So there are many organizations within an individual company who need to be able to authenticate to one another. The problem with well, we'll just unify it all at the root is it requires these multiple hop, you over there in another organization do something, so you can do something, so you can do something, and it's slow and it's expensive and it always blows up in our faces. Passwords. Just freaking work. It's a string of text. I can't emphasize enough. Everything I just described, or some letters. Okay, screw it, there's a $sign. It's just some letters. And that's how we end up with 61% of compromises coming from just some letters. So, if that wasn't enough, we have an entirely separate problem. And this one is actually more embarrassing because this is something that X509 tried to address. In fact, most of the complexity of it is related to addressing this, but whoops, it doesn't actually do anything useful. So, delegation. Earlier I told you, the root, you don't have to deal with it every time you want to put something somewhere in DNS. The root delegates to VeriSign for COM. COM delegates to a horde of companies putting names inside of COM. It's the same with all of these things. And once you have these delegations, you just don't deal with layers above you. You don't really have that for certificates, if you notice. Every time you need a new certificate for your organization, you got to keep going back to VeriSign. You got to keep going back to Komodo. Oh, I got a new server. I got a www server. I got a mail server. I got a this server. I got a that server. Now, I bet you all thought that this was just because VeriSign wanted to make a lot of money. This is true. VeriSign wants to make a lot of money, but it happens to be the technology doesn't really let you do more. Well, first off, you don't really want to keep going back to VeriSign because it's expensive. You have to keep paying them. It's operationally inconvenient. You have to keep waiting for them to come back to you. You're telling a third party about your internal organization. And by the way, it integrates really poorly with devices. If I buy a router, I can't get the router pre-shipped with certificates that make it part of my company. I have to do some crazy dance where I get the company to bring in the device, set it up, and then the company goes to VeriSign to get a certificate, and then VeriSign talks to me, and I click the link, and then I give a certificate to the company who's setting up the device, and at this point, you end up with every device in the world has self-signed certs. That's where the story ends, and we all see it. This is why. Now, what you should be able to do is just get a certificate that says, hi, I've proved this guy is docsparrow.com. He can sign a cert for www, he can sign a cert for mail, he can sign whatever he wants, and he doesn't have to come back to me all the time. This would scale beautifully. This is not something X509 lets you do. It should. X509 has the concept of intermediate certificates. That's when the root, VeriSign, says, I don't want to have to re-sign stuff all the time. So I'm going to give this chunk of the namespace to you. Here's star.docsparrow.com. You can sign whatever you want as long as it ends in docsparrow.com. And this is what name constraints are supposed to do. Name constraints being a component of X509 v3. It took them not one, but 2 revisions to realize this might be an important feature. It's not supported to any reasonable degree. It's an optional extension. So what this means is, if someone gives you an intermediate certificate for docsparrow.com, the thing won't work. It's just not really going to work for you. You can also get a certificate for star.docsparrow.com. And now you get to put the same key on all devices throughout your organization. Here's the technology that was supposed to make it so we don't have the same password everywhere, and now we're going to put the same key material everywhere? Are you joking? DNS doesn't have this problem. The root delegates to VeriSign, VeriSign delegates to my servers. I can put whatever I want in docsparrow.com. I don't do anything with VeriSign. I don't do anything with the root. I talk to my box. It's great. Now, you can painfully delegate with X509. And here's what happens. A company spends some huge amount of money on their internal enterprise certificate authority because they drank the Kool-Aid. And this still happens today. Like, we knew this was broken in 2002. This is still best practices in 2009. It happens to be the best way to solve the problem right now, which is why we've got to do better. Now, I'm just watching clocks here. Okay. You can't do delegation securely without name constraints. So what do people do? They do it anyway. At least, we have some very cool, very elite attacks against X509 certificate authorities. We'll talk about them. But you know what else you can do? You can just walk up to a certificate authority and say, yeah, so I spent a lot of money on my CA, and it doesn't work with anyone outside of my company. Here's a pile of money, and I promise to be good. No, really, the heart of, you can just buy a root certificate effectively. It's not expensive, it's not that difficult, and there's an unknown number of companies out there, not just the certificate authorities, but all of the companies that have intermediate certificates. They can all issue certificates for your domains. How did we screw this up this badly? So, it's not that the companies, a lot of people love blaming the certificate authorities. They do. They love saying, oh, evil VeriSign, evil this, evil that. You know, why don't they do the right thing? Look, I have spent time talking to all of them. They all do the best with what they have. But I'm telling you, what they have, this is the best they can offer. Name constraints is not reliable. There's customers who have huge networks, they require intermediate certs, and everybody can issue the same intermediate. People just shrug their shoulders and say, fine, we'll take the payday and hope for the best. What are they going to do? It's the best the technology offers. And that's why we need better technology. So, this system is starting to fray pretty badly. 2008 in particular was really not a good year for the X509 certificate authorities. Mike Zussman went ahead and bypassed Komodo's security checks by saying, hey, you know, I have this internal server and it's called www.live.com. And they're like, okay, well, it's internal. It can have whatever name it wants. God damn it. Well, when I hacked DNS, I happened to also hack the DNS query used by domain validators. And it wasn't just me. I mean, that year I hacked DNS. Avi Pilosov showed how to basically effectively interpolate BGP such that all traffic from a certificate authority would, instead of going wherever it was supposed to go, would go to him. Now, the difference between my attack and Pilosov's attack is my attack doesn't work anymore. His attack is going to work till the end of time. So the big hack of 2008 was Stevens and Sodorov's work against MD5 that was actually presented here. And this was really cool work. So the deal is, and it gets a little more technical finally, when a certificate authority, a country, deems you worthy of a certificate or a passport, it signs, creates a passport with a hologram, your public key, your photo. Now this signing requires two steps. First, it requires securely hashing the certificate. This is creating a summary. You don't sign everything. You don't put your hologram on everything. You basically put your hologram on a summary of what is there. And the summarization work is called a hash. Now, the hash that a lot of people still use to this day is called MD5. MD5 has been known to be broken since approximately 1994. We're still using it. Crypto vulns tend to break in slow motion. So we knew in 2004 this thing was going to break. And basically every 2 years it gets worse. What Stevens and Sodorov found was that one of the certificate authorities, which since had been bought by VeriSign, RapidSSL, was actually using MD5 as its hashing algorithm. So when RapidSSL asserted an identity, it would summarize the identity using the MD5 hash. What the most recent and most interesting MD5 break actually came from Stevens and Arjun Lenstra. And what they found was what they call a chosen prefix collision attack. The idea is you have two files, and they have totally different beginnings, totally different content, whatever. So they're going along, they're totally different. Then you put a magic blob on, bam. And this magic blob synchronizes the hashes. So now, as long as whatever comes after is the same, the ultimate hashes will be the same. Now this means you have two different inputs with the same summary output. Meaning the certificate authority can think it's signing something saying, hi, I'm some big long domain name.com, but what actually anyone in the field sees is, hi, I'm God, and you can tell because RapidSSL says so. beautiful attack. And they, just to give them credit, they actually ended up having to do some like crazy stunts with the serial number that the certificate authority applied to that particular certificate and timed it out to the second so that it would all work. Those were actually really cool. So it turns out there's a lot more where that came from. X509 is not just bad from a business process representation standpoint. No, the technology is actually really bad in and of itself. It's remarkably fragile. At pretty much every depth that we have examined it, we have found significant issues. Consider hashing functions. MD5 is not the only deprecated hashing function in X509, at least in common implementations. MD2 is there as well. MD2 is the predecessor to the predecessor of MD5. There actually was no MD3, there's just 2, 4, and 5. If a certificate is signed with MD2 RSA, everything as of a few months ago, except for GNU TLS, will accept it. Now, this shouldn't matter, because Stevens and Soderov attacked MD5, and when they attacked MD5, they attacked it in real time, meaning right now, today, or at least right then 1 year ago, some idiot out there is applying MD5 to incoming certificates. Nobody has been applying MD2 to anything for almost a decade. So we shouldn't be able to do anything, right? Well, anyone here familiar with the Final Destination theory, Final Destination series of movies? Few of you. So in Final Destination, what happens is somebody kind of realizes death is about to come, wipe out a bunch of his friends, and warns everyone and gets them out of the way. And the entire rest of the movie is death getting its revenge by killing people in really spectacular ways, but slowly. Cryptographic vulnerabilities tend to be subtle and telegraph years, sometimes decades in advance. We don't know how they'll burn us. We certainly don't know when they'll burn us, but we do know we're going to get burned, and historically we do know it's going to be pretty epic. So the relationship to the Final Destination series is left an exercise to the reader. So let's start by looking at VeriSign's root certificate. Holy crap, it's self-signed with MD2. But it's okay. It's not going to be a problem forever. It's going to expire in 2028. Jesus. So, why is it signed at all? It's a root certificate. You don't trust it because it has a signature. You trust it because it's shipped with your browser. That MD2 certificate, that self-signature, no value whatsoever. Why is it there? Well, the best theory I have, and if you were there, you're welcome to say, no, Dan, that's crazy talk. But the best theory I have, having worked with a bunch of ASN1 libraries, is so ASN1 is the encoding underneath X509. And when it says, I want to see a signature, it's got to get what it wants or it errors out. So rather than making the certificate optional, the signature optional, I think the guys just said, I know, why don't we just self-sign? It'll be totally meaningless, but it'll stop the parser from complaining. And as everyone knows, more crypto equals more security. So this totally worthless thing from 1996 is sitting there with an MD2 certificate. why was it signed with MD2? I mean, didn't they have better options? Well, according to Gutmann, so when I say we didn't know much about security in the 90s, I'm not kidding. Like, we didn't know what the hell we were doing back then. According to Gutmann, quote, VeriSign were, as of March 1998, still issuing certificates with an MD2 hash, despite the fact that this algorithm has been deprecated for some time. This may be because they have hardware which can only generate the older kind of hash. So you have some like magic box, it's hardware, that means it must be secure, that issues a certificate, it's crypto, that way it must be secure, that is actually haunting us to this day. So I've been talking to you about MD2 and saying, hey, you know, it's there from 1996, and still, so what? You've got an MD2 thing from 1996. What are you going to do with it? You can't get anything new to sign with it, so you're not going to be able to do anything like that chosen prefix attack. How could you possibly think there's going to be an issue here? Well, it turns out hashes can fail in many different ways. One way they can fail is just a straight collision. That means I can go ahead and gin up two things that have the same hash. So I can't control any of these things, but I can say, hey, here's two files, same hash. And Xiaoyun Wang actually did this in 2005. This is what caused me to write my MD5 to be considered harmful someday paper, which led to last year's MD5 considered harmful today talk. I didn't like that at first, but then like after I got over it, I'm like, that's actually really cool. So that was, the collision attack was in 2005. 2 years later, we got this chosen prefix collision attack, neither of which are going to work for this particular use. There's another class of attack against a hash. And what this class of attack is called a pre-image attack. It says, I have this hash here. I need something else to have this hash. Something different. I may care what, I may not. But I've got this from 1996. I want to make something else today look like way back then in 1996. Pre-image attacks against SHA-1, we have no progress towards. Pre-image attacks against MD5, we have no progress towards. Pre-image attacks against MD4, we have no progress towards. Pre-image attacks against MD2 are another story entirely. It turns out we are getting pre-image attacks against MD2. If we were to get one, here is how you use that self-signature, which has no legitimate use, but here is how you use that self-signature to do something nasty. The first thing you do is you create a certificate declaring, of course, hi, I'm God. This is worthless, because why should anyone believe that you're God? You aren't signed by anyone, no one asserts it, and you're kind of full of it. Now what you do is you modify that certificate that you generate, and you give it the same signature as that root certificate from 1996. So now you have this new thing which has the same hash, and thus the same signature, as the thing from 1996. And then you say, hey, I've got this thing here, it's an intermediate. You know who's going to assert that it's real? The 1996 root. Well, what's going to happen? The browser's going to go ahead, look at the intermediate, and say, okay, this guy says he's God. He says he changed back to this 1996 thing. Does he have a signature from the 1996 thing? Yes. He has the signature of the 1996 thing. It works. What can I say? This does depend on there being an actual MD2 pre-image attack. How hard is that going to be? Well, in 2004, the complexity of this was 2 to the 104. In 2005, the complexity of this was 2 to the 97. In 2008, it was 2 to the 73. Now, our largest known computational efforts, not taking into account memory here, are 2 to the 63. Now, I'm going to show you a graph. Now, what do we do about this graph? We can do the normal thing and just say, well, there's not a problem now, and there's never been a problem found in 1994 that finally burned us in 2008. So why don't we just sit here and do nothing? Or how about we fix a crypto problem before it blows up in our face? Holy crap, they did it. It actually worked. So Openssl is like, forget it, we don't need MD2. Firefox is like, gone. Red Hat pulled it from their operating system. VeriSign's been doing a bunch of work. Opera actually has killed it. Apple's killed it. Microsoft's on the verge of killing it. Google removed it from their phones. Everyone basically said, this MD2 thing is crap. I don't need it. This is easy. This would have been such a bigger pain in the butt if it had happened like emergency because the certificate and the attack is out. But no, it was like, well, this is going to burn us. It's going to burn us sometime in the next couple of years. Let's take the next few months. Let's fix the problem. No drama. It was great. And here's the funny thing. It turns out that this certificate from 1996 has a little quirk to it. It doesn't just work for authenticating servers. Now, normally, SSL goes ahead and says, hi, I'm talking to www.docsparrow.com. SSL can also say, hi, I'm Dan Kaminsky logging in. If you have a break for the 1996 cert, you get to assert you are anybody from any company on earth to a secure web server. This would have been a problem. Now it is not. And this was actually not a trait that the 1996 thing had, or the 2008 thing had. Funnily enough, you can actually check to see if a given secure web server, A, supports client authentication, and B, actually trusts this particular certificate. There's something called a certificate trust list. And in SSL, the server will actually tell you, here are the certificates that if you could possibly generate a signature from, I will go ahead and allow you in. So it just volunteers this list to you. Pretty much every Windows IIS server configured to be secure will have the 1996 cert there by default. So, one thing as a takeaway, if you are running one of these secure servers, you might want to remove that particular one from CTLs. You can actually configure that. So, I've been kind of beating up on VeriSign. It turns out this wasn't just their problem. There's also, as of about 2002, Thought, who wasn't yet owned by VeriSign. They were also signing things with MD2. Now, this certificate has expired by now, but it turns out that a few people still have their old expired certificates on there. And I was actually really amused to see that one of the groups that still had a signature was named Rubicon, given that Rubicon was an American con that ended in some interesting scenarios. So, question. Didn't this need to be completely and utterly fixed immediately? No, because we're going to have some time before the actual MD2 attack comes out. Who knows? It might take a few years. But we went ahead and asked, and it was like, hash research is progressing along. We'll eventually break this, but don't worry. So, is that all we can do? Oh, God, no. It's X509. This thing has tons of fun. So, there actually are many more things that we can do against X509. Is it possible to use X509 issues to bypass protections in present-day certificate authority operations? So, yes. And the way we're going to do it, so I actually had a couple of co-authors work with me on some of this research. And what my friend Meredith Patterson told me was, this is last year, we were talking about certificates. Was this last year? Yeah, this was last year at CCC. She says to me, I'm going to go home and figure out the precise grammar of a certificate. I'm going to figure out what I can put in there and how people are going to interpret it. Certificates are not just simple sequences of bits. These are complicated objects that have complicated languages. Like, will everyone parse the same thing in the same way? I thought about it, like, no, there's no chance. There are patterns to security. One of the patterns of security is if you have a whole bunch of complexity, you're going to have a whole bunch of vulnerability. Certificates are fundamentally complex objects. Now, there are two kinds of vulnerability that you get from complexity. One kind is what I call traditional exploits. You cause the system to misuse memory. Inside of a certificate, you have large numbers of overlapping length fields. Overlapping length fields in a file format tend to instantly mean to a vulnerability researcher, okay, every parser is going to blow up. And in 2002, every parser did. 2002, SNMP was fuzzed by a company by the name of Cryptonomicon. Actually, no, it was fuzzed by the Protos project at the University of Jooli in Finland, who then went ahead and forked off this company, Cryptonomicon. They destroyed everything because ASN1, the underlying encoding for X509, and for SNMP, is a big mess. So all they did was throw random crap at it and blew up everything. But there's a second class of vulnerability, and this is something that hasn't been looked at much in certificates or in any of these ASN1 systems. And those are semantic exploits. This is when one person reads one message, the other person reads the other. Remember the attack from last year? One person thought they were signing, "Hi, I'm just some nice, innocent person," and the other person received the message, "Hi, I'm God." So there is actually a language going on. There's a communication going on. And Meredith refers to this as language theoretic security, and I kind of like it. A CA and a browser talk to each other. The CA says, "Browser, I tell you this public key is linked to that subject name." The browser says, "CA, I hear that this public key is linked to this subject name." You want those subject names to be equal. You do not always get what you want. Now, here's the pipeline. This is what happens inside of a certificate authority. The user generates their public and private key. They submit a specific form of name called an X509 subject name with the public key. And what I told you earlier was a PKCS10 request. Now, there are many pieces of information inside of this request. There's name, there's city, there's country, there's state, there's organization, there's organizational unit. All of this stuff is crap. Part of an alternate universe that never actually got implemented. The only element that browsers actually care about is called the CN. It's the common name, and it's ultimately why all the complexity of X509 comes down to, well, we'll trust DNS. So if a certificate authority approves of the common name, meaning they go back to DNS and everything looks good, they can do one of two things. They can either generate a certificate with the known good parts, or they can just say, everything looks good, I'm going to sign the subject name as it showed up in the request. It turns out OpenSSL makes it really, really, really easy to just sign the request as it came in. So you go ahead, you get this request, and you say, hey, look, it all looks good. And so one thing you do is you just sign it, and then you audit the text that comes out to make sure that you approve of this particular subject name. So CN equals www.foo.com. Yeah, that looks fine. I'll send that back to the user. This just works. Also, you can dump the request to text and then go ahead and audit that text. Also, you can dump the certificate and audit the subject. So these are all things that OpenSSL makes very, very easy. They're also all completely insecure. So I'm a big believer in secure by default. If you have a framework that really tries to blow up in your face, it's going to blow up in your face in the field. So one thing you can do is you can say, I have an organization name of Bad Guy Inc., /cn equals www.badguy.com. That would actually show up in the ASN1 tree. And when you actually do the dump, you see O equals badguy inc /cn equals www.badguy.com. There's no way for the text parser to know, oh, this CN didn't come from dumping the ASN1 tree, this CN came from just the organization. Now, there are command line modes. In fact, all the alternate command line modes fix this problem. However, the default one is the one that's insecure. Crap. Now, the exploitability depends on how the text auditor handles multiple common names, because there's going to be multiple. There's this first one, www.badguy.com, and then there's this second one, www.bank.com. Which comes first? Which is the one that is trusted? Well, this is a problem for a text parser. This is also a problem for the certificate authority itself, because inside of an X509 public subject name, you could just have multiple common names. They could just be there. You know, you had an organization, so you have an organization, you have a city, you have a common name, you have a state, you have another common name, you have a organizational unit, you have another common name. You can just like throw multiple ones in there. What happens? It's a good question, actually. So I went ahead and looked. Well, it turns out that it totally depends on implementations, and all possible answers are implemented somewhere. OpenSSL trusts the first. Crypto API inside of Internet Explorer is all-inclusive, so if any CN matches, and Firefox takes the last. And the RFC says nothing. It has a two-word parenthetical that says use the most specific one without actually defining it. So the definition first, all-inclusive last. The definition actually is fail. Now, OpenSSL does not necessarily only return the first one. If you use the API in this particularly documented way, okay, if anyone ever tells you we had a security problem, but it's okay, we wrote some documentation and now it'll never be a problem again. I've heard that recently. So it's possible to use OpenSSL's API to do things securely, but no, everyone just uses this X509 get text by NID call. You see this in Clause and Open1X and wget and Bacula and Neon and Openssl Api. Pretty much everyone just only returns the first common name. So if you have a CA that's using X509 name get text by NID, you're only going to see or validate the first common name. So how would you build the optimum exploit for this particular scenario? Well, it turns out you can have wildcards in a certificate. Netscape, if you have a cert for star, simply works for all names. It's the other way to say you're God. Internet Explorer, I gotta give them credit, they basically say, if some CA was stupid enough to issue this, I ain't touching it. Nice, that's great. So IE is chicken, they're only accepting wildcards if it's at least 2 labels in. So what you do is you have your first common name, www.attacker.com, and that's the one that OpenSSL leaves. And then you pick up a couple of websites, you can have however many you want. These are the ones in the middle, and IE gets those. And then you just throw in a star at the end for Netscape. So, now let's talk a little bit about ASN1, which I've kind of been hinting towards you guys. It's designed to be very fast to parse. It's actually very fast to crash under fuzzing, as I mentioned earlier. Every certificate authority has an open ASN1 listener, which for the love of God, I hope was actually fuzzed from the SNMP work. Because if not, it's a really big open port. So it is It turns out these requests are a channel for SQL injection, not just ASN1 attacks, but SQL injection. And it turns out little Bobby tables help secure the internet. Like, I was talking to Peter Goodman, he's just like, yeah, we saw this comic and we're like, oh, someone could do that to us. I thought I was being all late with this. Like, no, this happened 4 years ago. Big panic. But it turns out ASN1 itself has some stuff. So ASN1, common name is not expressed by COMMON space NAME. It's also not expressed with CN, because that would be easy. And to be fair, very Anglo-centric, whatever. So they said, you know what, we're going to make something that is just as confusing to everybody. And instead of common name, we're going to use the number 2.5.4.3. Now the question is, how is this encoded? How do you actually get, is it a number 2, number 5, number 4, number 3? No, that's way too logical. What we use is another layer underneath ASN1. See, ASN1 is the abstract concept of a tree. We still need to get to bytes on a wire. So the way bytes on a wire are encoded in ASN1 systems usually, it's called BER, Basic Encoding Rules. And BER is a tag length value system. So you say, hi, I have a type 30 message of 50 bytes, and here's 50 bytes. And there are going to be things inside which themselves are tag length values, and it's a big stack and a big mess. So OIDs, or object identifiers, have a tag of 6. Now I have to apologize, I'm totally going bitwise because it's the only way to understand this attack. Numbers are encoded in base 128. So what this means is that you have, base 128 takes 7 bits. So you can express from 0 to 127, and then the question is, do you have another digit? Like, going from 9 to 10 takes another digit in base 10. Going from 127 to 128 takes another digit in base 128. So what you say is, let's say you have the first number is 6. You could say, I have a 6, and that's just 06, and there's going to be a dot after this. Or you could say, I have 86, which is 6, and now there's another digit. Like 1, and now there's another digit, and that's 0, so now my total number is 10. So a simple object identifier, 2543, has a tag of 6, a length of 3, and values of 55, which is 2.5, and do not ask me to explain why. You'll cry. Yes, they did bit compression because you couldn't possibly use 2 bytes to express what would conveniently be 1 byte. Why? So, they have an incredibly stupid, I never thought I'd see stupider compression than DNS, but. So, okay. So you have 55 for 2.5, and then just a 4 for 4 and a 3 for 3. Very nice and simple. A more complex object identifier would be 1.2.840.113.549.1.1.1. Believe me, when they go crazy, they really go crazy. And yes, I'm watching the clock, making sure that I end this on time. So, tag 6, length 9. Now look what happens here. We have 8648. That means 6 times 128. Okay, that's larger than 80, so there's another digit. And 48 in hex is 72, so we get 840. That's how you end up encoding numbers in base 128 and expressing place value. You're using a bit to say there are more bits in this number. Works very well. So there's some ways of playing with this. The first thing you can use, and I think I've seen this before in LDAP, but if someone remembers, could you tell me? Because I don't know who to cite. I just know I've seen this before. Let's say you had leading zeros. You have a tag of 6, a length of actually 4. I got this wrong. 254. And what if instead of just a 3, we do 8003? Well, now we have 0 times 128, which is still 0, plus 3. This is still 2543. It's just a different way of saying 2543. Wouldn't it be tragic if we had that in a X509 subject name as merely another field to ignore? What if this got through? Well, OpenSSL basically says, I don't know what the hell that is. That's good. NSS will actually parse it as 2543, but it will not say common name. It will say, I have an object identifier, it's 2543, but no, it's not common name. Internet Explorer is like, cool. This one made me really happy when it finally worked. Theoretically, numbers in ASN1 are infinite length. You can express 2 to the 5,000. In reality, ASN1 parsers are implemented on hardware, and hardware has limited sizes to the numbers that it likes to represent. This is usually a problem with memory allocation. I actually have a semantic equivalent. So what if we express the number 2.5.4.2 to the 64 plus 3, which actually looks like this with all the zeros and the 2 and so on? Well, OpenSSL actually runs on a big num engine, so it is not fooled in the slightest. Netscape overflows, but not exploitably, because it also says the 2543. So that was kind of sweet. Now, realistically, most certificate authorities do extract the common name and throw away the rest. At least now they do. And that's good. Is there anything else malicious that we could get into the common name? Could we get something in that they really can't throw out? Well, a common name, you have an object ID, and you have an actual value, the ID value pair. And it's a printable string, usually. Say www.docsparrow.com, and that's just ASCII text. Well, the first thing to know about ASN1 is there are 13 different string types. Tragically, OpenSSL did not have this part. Like, I was messing around with them, and OpenSSL segfaulted. And I wasn't even trying. That's like the best feeling ever. It turns out it was not exploitable. If you have string types that have to have 4 characters each, so they have to be some offset of 4, or at least if they were legitimately generated, they'd have some offset of 4. In my case, I basically was able to get it to jump over the termination byte. And in any normally written system, this would be game over because it would copy into memory, but it turned out that OpenSSL has them, for once in its life, had a paranoid design and was not exploitable. Now, here's the thing. There are many ways of ending a string of text. ASN1 has an explicit length field, so this is 15 bytes long. And most C APIs are null terminated. So if the string ends with 0, it says, okay, this is the end of what I have to parse. So if you have a certificate that says, say, www.defcon.org, null, www.oxoo.com, OpenSSL is going to think, oh, that's part of the oxoo.com. I better check out that owner. But it turns out the certificate is parsed by every browser as www.defcon.org. So this was actually found by Moxie Marlin, Spike, and I. And amusingly enough, we exposed it at the same conference within like 3 minutes of each other. So for all the things you've heard, sticking a null in was actually the most reliable attack. And I could have gone ahead and gotten a cert for star.docsparrow.com, and that would have worked on everything. So the null one was actually fixed all over the place. Pretty much every browser on the planet no longer accepts stars. We're finding various like mail servers and mail clients, and it's a mess picking up all the things that hit nulls. So, but it's better than it could be. Anyway, long story short, since I've only got a few minutes before I got to give up the stage. Got 5 minutes? Okay. What do? There is a point with the technology that you just say, this thing has been failing so badly, so frequently, so messily for a decade, we have to do better. The reason I changed my mind on DNSSEC is not because I think the technology is beautiful, because it's kind of messy. It turns out, underneath all the messiness, there is actually a workable protocol inside. And that workable protocol just doesn't have all this complexity. There's no ASN 1. There's none of these delegation problems. There's none of these exclusionary problems. We were already basing our security on DNS, so it's no big change to use DNSSEC. We're already there. If your DNS is hacked, you're in a lot of trouble today. There's no deviation. The reason I want to see DNSSEC actually get deployed is because at the end of the day, instead of having this huge impedance mismatch, huge extra technological layer, all of this work, I just want to write a line of code that says, give me this person's PGP key. Give me the IPsec key for this IP address. Give me the SSH fingerprint. I want one line of code, and I don't want to have to think about OpenSSL again. That's what DNSSEC, done right, is going to be able to do. What I showed you today is a technology that has spent 10 years not solving our authentication problems. In about 6 months, the root is going to be signed, and a couple of top-level domains are going to be securable. I don't know if .com is going to be. I do know that .org is going to make fun of them every single day until they get on board. So I think they'll actually figure it out. Here's how what's going to happen is very simple. Big guys are not going to be able to move fast. We can code whatever the hell we feel like. So my hope is to see over the 6 months after the root is signed that we actually start seeing bubbling up, bottom up, interesting secure technologies that before we never could have written because frankly it took so much work and so many teams and so much knowledge. But now all of the hard security stuff is just going to be a single line of code. I need a PGP key. You don't have to figure out OpenSSL, you just need to run this one line. So go write cool stuff once we get the root signed. That's what I got.
Dan, did you want to take maybe 1 or 2 questions?
Yeah, I could take some questions.
Okay, if anybody has a question, please use one of the microphones in the aisles. Do we have any questions? Yep. Yeah. And just guys, a reminder, if you are exiting, because we still have questions, please exit as quietly as you can.
Hi.
Okay, go ahead.
I don't really have a question, but I think a nice remark, because you also mentioned Startcom. And I was evaluating Startcom as a way to certify test servers and everything, because they have these nice, cheap certificates for nothing. And what they do is they always add a subject alternative name of your pure domain name. So if you certify mystupidtestserver.mycompany.com, they add mycompany.com to the certificate. So if your silly test server gets owned, the hacker has a certificate for mycompany.com.
They add a star.mycompany.com?
No, just the domain name, but many people use the domain name without www for the main server. So if your main server operates at mycompany.com, the certificate from the test server.mycertificate.com will work for faking the servers that OutWs.
Thank you. I will poke Eddie Nig about that like today.
Do that. I was too lazy to do it.
The StartCom guy is actually really responsive and friendly.
Yeah, I know that, but
No,
Just
no,
depends on
dude,
that.
thank you. That's great.
okay.
So another question. The root is about to be signed, and that's basically good news. There are some problems also in DNSSEC. First of all, are you familiar with one or more alternatives to DNSSEC that are also about securing DNS? In particular, I'm thinking about DNS Curve.
So DNS Curve has no code, which is sort of a problem.
Yeah, it is a problem, and it's also, I mean, it's a problem that it's a bit late in time. Do you know of any other alternatives?
At the end of the day, nothing is valuable unless we get the root to play along. Like it's just worthless.
Yeah.
And this applies to alternate DNSSEC models as well.
Yep.
Like they've tried these things with like you do administrators FTP, they download these trust lists and they hope they keep them in date. It's a disaster. It'll never work.
Yeah.
So the only thing that works is A, get something into the root. DNSSEC is the something that actually has a chance of getting into the root. Turns out what the root does doesn't matter that much. What really matters is the realisticness of companies getting their end domain signed. And what I keep telling people is it has to be as easy to sign your domain as it was to apply the patch for my bug. So it wasn't that patching port randomization was easy. It was a big pain in the butt for a lot of people. But it was one pain in the butt and not a pain in the butt that went on and on and on. And my judgment of DNSSEC is that it's actually possible to do that, just not necessarily with the code we had in 2008.
I agree. And a follow-up question is, do you think that we will see, or that we should prepare ourselves for having a shorter life cycle of authentication technologies?
Well, I think we've basically had only one authentication technology that's worked, and that's passwords, and everything else has never actually started living.
Sure. The question is, will DNSSEC be good for as long as passwords have been good for some value of good?
I think we're going to see, and kick me off stage if I'm on too long, guys, but I think we're going to see some growing pains with DNSSEC. I think it's going to take at least a year or two to really get the kinks out. But it's one of those things that structurally is better. Like X509 has these structural flaws which guarantee it will fail.
I agree.
And DNSSEC, it just happens not to have those flaws. The thing to realize is DNS has been a working delegation system for 25 years and a working exclusion system for 10.
Yep.
And that level of success, I wish authentication worked as well as DNS did, because mostly DNS just works.
Oh, guys,
Thanks.
because I'm sure you'd like to ask more questions, and we actually have a long setup time.